Good morning, students. I, Mrs. V.A. Yavle, Assistant Professor in Department of Electrical Engineering, would be discussing with you all today one more numerical on axial mechanical force. In the earlier lectures, we have seen numericals on the radial mechanical force. Let's see how to continue with the numerical on axial mechanical force. Students, let's see one more numerical on mechanical forces. In the earlier lecture, we had seen a numerical on how to calculate the radial mechanical force under short circuit condition. Let's see one more numerical on the same. A 575 kVA, 7500 by 435 volt, 50 Hz, single phase, core type transformer has the following data. Width of the HV winding is 27 millimeters. Width of LV winding 23 millimeters. Width of the duct 15 millimeters. Height of the coils 0.35 meters. Length of mean turn 1.25 meters. Number of turns in the HV winding is 190. Per unit impedance 0.036. Doubling effect multiplier 1.8. Find the radial force under short circuit condition if the LV winding height is equal to the HV winding height and the instantaneous axial force on HV winding due to asymmetry if the HV winding is 5% shorter than the LV winding at one end. Now let's see how to begin with the numerical. The first and foremost thing that we are supposed to do is see that all the units are in their standard form. So this is 27 millimeters, which can be very well written as 0.027 meters. Width of LV winding 0.023 meters. Width of the duct 0.015 meters. Height of the coil is already in the standard unit. Length of mean turn is also in the standard unit. This does not have a unit. Per unit impedance does not have a unit, and doubling effect multiplier is 1.8. Now let's proceed with the numerical. The first step always is to calculate the rated current. So the first step is to calculate the rated current. The kVA rating of the transformer is 575 kVA. So when you multiply this by 1000, it gets converted to VA. Because it is a single phase transformer, it will directly be only divided with the HV winding voltage. When we calculate this, it comes out to be 76.67 amperes. Now, the second step is to calculate the current under short circuit condition. So, we'll just say the current under short circuit condition is given by, it is the doubling effect multiplier multiplied by root 2 into the rated current divided by the per unit impedance. If you see the numerical, students, the doubling effect multiplier which is given to us is 1.8. So we'll put the values in this and we'll get it as 1.8 into root 2. Rated current that we have calculated is 76.67 multiplied by the per unit impedance is 0.036. So the short circuit condition current comes out to be 5421.387 amperes. Now let us calculate the radial force when the height of the LV winding is equal to the height of the HV winding. So we already know the formula. So the radial force is given by mu naught by 2 LMT upon LC into short circuit current multiplied by T the whole square. Now let us first see the various parameters which are given to us. So width of the HV winding is denoted by, if you see the HV winding, this is the primary one, correct? So the symbol for this is BP. Width of the LV winding is the secondary winding, so the symbol is BS. Width of the duct is small a. Height of the coil is capital L subscript C. Length of mean turn is LMT. We already know this symbol, students. Number of turns in the HV winding, capital T. Per unit impedance, epsilon x, and doubling effect multiplier is a constant. So we'll just put the values. Mu naught we already know is 4 pi into 10 raised to power minus 7. LMT is given by the value of mean turn 1.25. Height of the coils is 0.35. So 1.25 upon 0.35. Short circuit current is 5421.387 multiplied by the number of turns. Number of turns is given by 190 and we have to square it. Just put the values in the calculator and the answer comes out to be 2.38 into 10 raised to power 6 newtons. So this is one of the answer. Let's now see the numerical once again. Now this section, the second part, is something which is little bit different. It says we have to find the instantaneous axial force due to asymmetry. Right? So the formula here is going to change and we are going to proceed. The formula is the axial force due to asymmetry is given by mu naught upon 2 k IT square LMT upon 2 bracket A plus BP plus BS, where this K is known as the unbalance factor. Now, how are you going to get this value for the unbalance factor? Let's see the numerical once again. See what they have said. The HV winding is 5% shorter than the LV winding. So, the unbalance factor K is 5%, which is nothing but 0.05. Understood, students? So, we'll just directly put the values in the numerical. So, axial force due to asymmetry is equal to mu naught is 4 pi into 10 raised to power minus 7 upon 2. K is 0.05. I short circuit current is 5421.387 into number of turns is 190, the whole square. LMT is given by 1.25 upon 2 into A. Width of the duct is 0.015 plus BP is 0.027 plus BS is 0.023. So you have to just put the values, calculate it, and it comes out to be 3.205 into 10 raised to 5 newtons due to asymmetry. Right? So we can see how to calculate the radial force as well as the axial force due to asymmetry. I hope you all have understood. The only difference was the formula has changed a bit and we have a new factor which is known as the unbalance factor, which is given by K. Thank you, students.